At the beginning, I would like to say a couple of things about the purpose of the Whitney algebra, and in a sense, the broad landscape in which Whitney algebra arises. So I will say sometimes again the things that Henri told you, that it is important to focus what is the landscape and what is the aim or the initial aim of Whitney algebra. And in my opinion, please correct me, Henri. In my opinion, Whitney algebras are an evolution of the bracket algebra of White, of Neil White. And what is the purpose that Neil White declared for the bracket algebra of Matroid? He says that it is twofold. On the one part, it has a purpose for the study of Matroid representations. And second, the purpose is to have something like coordinates to do linear algebra on Matroid. So for me, these are the main purposes of the White bracket algebra and also of the Whitney algebra over Matroid.
The only thing I would correct there is to say that it is also an escape from the bracket algebra, because a lot of extra work was done filling brackets so that it could be expressed, and put useful stuff in just to block the holes there, and it really makes more sense as an algebra of pieces of space.
Absolutely, indeed. In order to understand the development from the bracket ring of White to the Whitney algebra, one can think to a development from the Cayley-Grassmann algebra to the Whitney algebra of the vector space. So you have to think that you have, for a vector space, you have the Cayley-Grassmann algebra and the development, which is the Whitney algebra, which is closer to Grassmann intuition. And on the Matroid level, you will have the White bracket ring of the Matroid and the Whitney algebra of the Matroid. There are analogies along rows and columns of this diagram that I made you to imagine. So here I have the papers of White, so if someone wants to take a look, here they are. And then I will give you, well, here there are also a couple of papers of the first work paper on the Whitney algebra of 2000 of Henri and Schmidt, and the second, the final one. And finally, here there is a paper by Andrea Brini and myself in which the relation between Cayley-Grassmann algebras, Whitney algebras, and the regressive product of Grassmann is studied. So your question finds here the answer. But we will talk about it, some things more. And another thing is that there is a strong connection between Whitney algebras and the study of the covariance in invariant theory, and in a characteristic free way. So there is a connection between Whitney algebras and the letter place superalgebras, which were used by Giancarlo Rota, Frank Grossens, and Joel Stein. And this connection allows one to use the combinatorics of tableaus in the Whitney algebra. And indeed, one of the most recent results in the theory is a result by Andrew Berger, in which he gives a basis of over the integers of the components of the linear algebra in terms of tableaus. Here is the paper in picture.
Well, and of course, in between there, the wonderful paper that you did with Andrea Brini to show that what Giancarlo said about the connection between linear algebra in the first days of our talking about it, said that it was you were talking about a letter place algebra in negative letters in positive places, and it took another 10 years
But indeed, Andrea,
to show it.
That's completely Andrea Brini understanding of the stuff.
He understood it very quickly also?
No,
No.
he understood.
Yeah.
And
Yeah.
after he and after
And then you wrote it up.
other people, but that's Andrea Brini. That's absolutely
really?
Andrea Brini
Okay.
that understood clearly the connection.
Okay.
And so, what I have half hour of time, so now 20 minutes or less. So, what I can do is to write down clearly the beginning of the story. And then we plan, I hope I will be able in these days to write down a LaTeX file where there will be written the things that myself and we, maybe not this week, the next, month or so. So, now I will be a lot specific and slow, just to give the definitions, the main definitions and the main facts. So, first, let's start from a set. And we will denote by n the cardinality of the set of finite. Starting from this set, we can consider what is the free exterior algebra over the integers over this set. Or in another language, I could say the free skew commutative algebra generated by S. Everything is always on the integers. So this will be the algebra generated by the variables, which are elements of S, subject to the anticommutativity relations. It means that AB is declared to be minus BA, and A squared is declared to be 0. I need this because I start from a set, not from a vector space. And then we can also consider the algebra tensor square of this algebra. And I remind you that the product in this, well, let's say, what are the elements, or what is the natural Z basis of this? Well, you consider a total order on the set S, and then the natural basis over the integers of this will be given by products of elements which are strictly increasing.
What role does K play in the definition?
Sorry?
You've defined S sub K of S.
Yes?
Where does K appear?
No, it's
No,
not
skew. No field, only the ring of the integers.
Okay, got it.
And so, natural basis is given by monotone, strictly monotone words. strictly increasing words. And so, but however, in any case, it is given by words. And so I will use symbols also for words. And here, the product is given. A nice example of this product was considered by Henri at the end of his talk. However, if you have here, what happens is that this relation that holds for elements of S more generally holds for words. I mean, if I write this as W, and maybe I can write A1, AB, then I will say that the length of the word W is D. And then, more generally, here we will have a relation that for words W and Z, you will have -1 length of W times the length of Z, ZW. Now, in this tensor product, you will have a basis which will be given by the tensor products of strictly monotone words, and the product is defined this way: W tensor Z times W prime tensor Z prime equal up to a sign is equal to W prime tensor Z prime. And the sign is the sign of the switch of these two. So the length of Z times the length of W prime.
Is that just a property of the tensor product, or is that
This is the definition.
That's definitely
The definition of the tensor product of these two algebras.
right.
And this is very natural in the super algebraic setting.
Yeah.
This definition. These are the beginnings of a super linear algebra in a sense. And more generally, we could consider tensor powers from the mth tensor power of this algebra for every n. So we have naturally a sequence of algebras starting from a set. And there is more, because there are connections between these algebras.
This set's got some sort of ordering on it, does it?
Sorry?
The set has an ordering on it?
Well, I need an ordering. I need an ordering if I want to give canonical basis for this and these others.
Oh, so it's not just an arbitrary set, it's a set with an ordering.
But if you want, if you want a basis of a vector space somehow, if you want to construct a basis of a vector space somehow, in order there must be, but that is not essential to the structure. And what turns out, however, that you will have a grading, even if you don't consider an order here, you will have a natural grading on this, like exterior algebra, you will have a natural grading on this, and so on.
You have to order it to write down expressions and stuff, but
Yes.
the ordering is not changing anything structurally up to us. The ordering is irrelevant. Right?
Absolutely.
Yeah.
Yes. And there is more, there are connections between these algebras. And essentially, and I will point out a connection between this algebra and this algebra. And that connection is the coproduct. So, let me recall what is the coproduct the basic coproduct from this algebra to the algebra tensor square. This coproduct can be denoted like this, and is an algebra morphism which takes, which on the unity, which takes 1 to 1 tensor 1, and takes the generators of this algebra to the elements A tensor 1 plus 1 tensor 1. And once you have given these initial conditions, that's completely defined. And what it turns out is that the coproduct of a thing like A1 AD will be a sum of all the possible splittings of these two words, of this word into two subwords. Let's say something like AI1, AIE, tensor, AJ1, AJF, plus or minus. So this is a subword, this is the complementary subword, and this is the sign that you need to rearrange this like that. So this is, and so this is the connection between this and this. But more generally, there will be a connection between skew of S and skew M to the tensor. The tensor power, the empty tensor power skew of S. And maybe we can define it like delta M. So this will be delta 2. And then one could say, well, in all these expressions, these lengths are variable. So I can consider the sub-expressions in which the first fold has a given length and the second has another given length. And so you will find these slices that Ari was talking about. And so, for example, could have also something like here L EF for given E and F, and more general conditions. But it's just to connect what I am saying to what Henri was saying. But this is not the main point of my talk.
So that morphism into the M-fold product, if you applied it to a generator, you'll get...
Oh, you will get
A
the
cross
sum
1
of,
cross 1.
yes, all ones,
Yeah, all
and
ones.
just one.
With one, with the generator occurring once in each
Exactly,
location. Yeah.
that's it. That's it.
It's almost Buddhist. That one is a non-zero word of length 0.
Now, let's consider a structure on the set S. So we will consider a Matroid on the set S. And we will see what is the natural development of this.
I think I need to sit on the floor.
Show this boundary operator.
Hmm?
Can we show this boundary operator?
They will show up shortly.
Yeah.
So let M be a Matroid on the set S. as before, we denote by n the cardinality of S, and now we denote by R the rank of the method. And so, in analogy with, well, or we can start from the skew super anticommutative, the skew algebra over S, and since S is a Matroid, it is natural to consider as zero all the words A1, AD. But I mean, if the set A1, AD is dependent set in the Matroid, then it is natural to set this equal to 0 in our structure. Also, if there will be a repetition on this, it will be automatically 0. So, when we mod out by these relations, we will get a new algebra, which is closer to the Matroid structure. We denote it by W1 of n. Now the question is, when we go to the tensor square of this, what are we going, how can we use the Matroid information? Well, let's consider skew of S, tensor, skew of S. Now we can use the coproduct. So we start from this equation, and then what is natural to set the coproduct, the second coproduct of this word equal to 0.
Couldn't you just take the tensor product of W1 of n with itself? Does that give you the same algebra?
Sorry?
So take W1 of n.
No. It's not up. You have really a good point. A deep point is not. This is not enough.
Yeah.
This is not enough. They are so. From this fact, it turns out that while in the case of a set, you have indeed an Hopf algebra. The Hopf algebra starting from the skew algebra. Now you will not get an Hopf algebra, but a relaxed Hopf algebra, a lax Hopf algebra, as Bill Smith worked it out. Okay?
On this delta, have you defined this delta?
Yes, it is the coproduct which goes from here to here. So
That's an S, not a subset.
So what you are going to set equal to 0 is that sum of A, I1, A, IE, tensor IJ1, EJF. This will be 0 here, and you will mod out by these relations. Now, there are many things to say, but maybe I think that it would be nice to see how the Kramer rule can be derived in this way in the method. So, going at one level of discussion of one of the two aims that White declared. One was representation of Matroids, the other was linear algebra on a Matroid. And that's interesting, I think, to see how the Kramer's rule shows up naturally in this set. And however, before doing that, let's say a couple of words about Matroid representations.
You have delta 2 there, so is it just?
It's an S.
It's an S. It's
Oh,
the morphism
delta.
into the tense product of S with itself.
Of the skew.
It's
There was a
delta
delta,
S.
there was a delta before.
No,
It's
sorry,
a delta.
So you.
It's been a
you-
delta
Delta square.
thing.
Oh, delta square.
Just
You're
a square.
applying it twice.
yes, oh, well, so here we are defining the second,
It's
Whitney
the same
algebra,
set as a multiple.
the second Whitney algebra of the Matroid M will be this mod out by this delta square, the second topology. And more generally, you will have Whitney algebras of level M on the Matroid M, which you can imagine. So you have again a sequence of
Okay, thank you.
algebras. And there will be also co-products between these and these, but that's more difficult. So I'm not going to talk about it. That's the lax of algebra structure of Schmidt. And now a couple of things. Oh, but they are almost over. They are over. It will take something like 10 minutes to it's fine? Okay. So, what about representations of the Matroid? What happens is that if you have the representation of G of the Matroid M, given of the set S, into a vector space of a field, not a skew field, because we are doing multilinear algebra, and multilinear algebra over skew fields is not so easy. Maybe not so natural. K over field K. Then, what happens? It happens that here you will have a sequence of algebras, the Whitney algebras of the Matroid. And here you will have the tensor powers of the exterior algebra of the vector space. Before I used the symbol skew in order to make a distinction between things done on a set and things done on a vector space. So, and what happens is that this map of sets will give a sequence of maps of algebras. From these algebras to these algebras over the integers. So it means that this is over the integers, this is over the field, but you can forget finally that it is over the field and consider only the structure of a Z algebra. And there is a theorem, a characterization of representability of Matroids given by Greco and Schmidt, which is the analogous of the characterization of White of representability. The condition is that whenever you consider some words which come from independent sets, so briefly some independent words, and you consider the corresponding element in these algebras, they will have to be different from zero. If you want that your method could be coordinatized. The strong fact is that the converse holds. So the method M is coordinatizable if is representable over a field if and only if that condition holds.
I have never seen an example of the converse.
I did an example.
Oh, okay.
I gave the computations related to the Desargues configuration in the Whitney algebra.
Okay.
And finally,
Lovely.
4 years ago, somewhere,
So you actually have a
tested
product
this-
of brackets equal to 0.
Yes, there is
Oh, yeah, wonderful.
not of independent.
Yeah.
So, this is for representation. And now, let's look for the Cramer rule in the Whitney algebra. So, consider a basis of this Matroid. To that basis, so let V1 D be a basis of the Matroid. So these are elements of the set. And consider an element V0. Yes. Now, what does this mean? We will work in the second Whitney algebra of the method. That will be enough. Our discussion will be here. And also what some hypothesis, the hypothesis will be given here, and the statement result. So, what does it mean that this is a basis? Well, maybe we have to write here R, since it is the rank of the Matroid. And then essentially is the fact that this is independent. And we assume that this is representable. Assume that M has representation. Well, let's see where this hypothesis shows up. It's important to do things without that. So, indeed, we know exactly that in this algebra we will have V1, V are different from 0. This monomial will be different from 0, because here things are simple. A word is different from 0, it comes from an independent set. A word is equal to 0, it comes from independence. Things are more subtle here, but they are simple. So this is our hypothesis. And then also, since this is a basis, in particular, what happens is that V0, V1, VR will be 0. Because this is a dependent set.
V0 is not in the basis.
Yep. And now, what can we do is to consider the coproduct of this word. That will be 0. And also the slices, all the slices will be 0. So, we have that the second coproduct, slice 1R of V0, V1, VR. This has to be 0. Now let us compute what is this coproduct. Here you have to consider, let us write it. This is the sum of things like, in the first fold we will have just a vector, just a point, let's call it Vi. And so on the other side you will have everything but not Vi. So V1, V2, not Vi, Vi. And here, what will be the sign? It will be -1 or V0. Started from 0.
-1 to the power I.
Exactly. That's it. This has to be 0. Now, let us write it more nicely, because this is special, this is not like the others. So, you will have a summand where the 0 is on the left, and the sign is plus. Plus. There, you can write things like this. You can write -1. Well, the sign will show up after vi tensor v0 v1 not vi vr, and here I that goes from 1 up to I. And then the sign here will be, well, -1 to I, but we can make something interesting. We can move V0 in this position. It's nicer, a nicer position for V0. So here, what you have to consider, you have to switch I-1 positions. So you will get a minus here. So you will have V0 in position I, and this one. Well, since I have not so much time, you can guess that you will have something like V0 tensor this equal to this one. This is coming so in the Matroid. And when you use the representability, you will have this relation in the exterior square of the vector space, and then you can use brackets to make this thing scalars. And you will get really the grammars. And
Are there any questions?
Yeah, this is a complicated question, maybe, but if you start to get bored with it, just shut me up and we can talk about it later. I inherited this master student, and it's the last thing I ever wanted to do. But what she was doing was, she was halfway through her master's thesis on this thing called the Kovenov homology of knots. And it was really horrible and complicated, and I didn't like it at all because I had to learn new stuff. And learning new things, you know, the brain sort of desperately tries to avoid anything except learning stuff. But in the end I did it, and I actually found it was really interesting. But so what it was is that it's a way of associating an algebra with a knot, very much like what you've done. And it's a graded algebra, and you look at the various gradings, and there are natural co-products that give you,
absolutely.
that give you, and then you can sort of sum the various parts, and then you get a chain complex with a natural differential. And if you look at this, the chain complex differs according to the same knot, but because it's all done from a projection of a knot. So the same knot will give you different chain complexes, but the homologies don't change. So the homologies of these chain complexes becomes a knot invariant. And the actual, if you look at a chain complex, what's it called? It's got the Euler characteristic. Chain complexes have Euler characteristics. And the way it's all set up is if you take the Euler characteristic of the chain complex, you get the Jones polynomial, which is, and so, you know, this was a lot of stuff for me to learn. It was really painful and I hated it, but now I've learned some of it I really like.
You could probably get a master's degree out of that if you wrote it down.
If you give me a reference, I will also.
Yeah, but what I think is the interesting thing is that, so, I mean, all of the moves, when you start to look at how you do these computations, they're so Matroid theoretical, because removing crossings is just like deletion and contraction in a Matroid. And so I was wondering whether or not, I mean, and you know, the algebra is all of these products of vector spaces and things like that. So you know, this chain complex is actually very much the algebra underlying this. They're very much like what seems to be going on here. The trouble that I was trying to sort of mix these two worlds. And I'm just wondering whether there's something that you could do here as to whether associated with the Whitney algebra or something like that. These Whitney algebras for a matroid, you could get gradings and sort of do something and then get a similar thing, a chain complex. And then you could actually say some of the homological invariants would be telling you something about the potential for representing the matroid in different ways. And the question of whether or not you got something like what the Tuck polynomial could come out as which is, so anyhow, I just thought that's
Very nice.
I think that could be the, so it just all seems to be very interesting. There's a possible thing to,
Those ideas.
One possibility is the hierarchy of matroid of circuits, matroid of circuits.
absolutely, yeah.
And that is very common.
Yeah, there's
So,
something.
If I understand all this correctly, it's possible if you compute in the second Whitney algebra, you sometimes use rules that you derive from the first one, and at other moments you really need the rules that are defined for the second one, right?
Can
So
you repeat?
So you have all these algebraic relations,
Yes.
but some of them, if you work in the kth Whitney algebra, some of them already exist in the k-1 algebra. So there's an homology there.
Yeah,
There's-
that's right.
Oh.
And I think, I know a characterization of planarity for graphs that essentially says that you pick up extra generators in sort of a second order algebra as soon as you include K5 and K3 as a minor.
Mm,
And something like that might be going on here.
mm.
You perhaps get minor closed classes saying, well, in the kth level, nothing new comes up anymore.
Mm.
So, yeah, perhaps that is what you want to...
Well, what I mean, the trouble is I just don't understand enough to be able to say, like, there's some, but the analogy between what's going on here and what's going on in what she was, what's going on in this Covenant homology is incredibly striking, and we sort of have a model for moving from knot theory to matroids via via the graphic representation of a knot, and I was sort of trying to think about that, but yeah, so the
You have a
trouble is
kind
I
of
don't
boundary
really,
operator, right? That
Yeah.
goes from the kth to the k+1.
yeah.
And,
That's
and
right.
if you
That's-
apply it twice, you
Yeah.
probably get
You
zero.
come up with zero. That's what.
Yeah.
That's what
So there
yeah.
really is
There really is.
homology, and-
Yeah.
Oh,
yeah.
I understand. Nice.
Yeah.
So the question is, at which point does this homology go trivialize?
Yeah. Yeah. And you see, what are the invariants? That's the.
Well, one other question I had, so earlier on you spoke about representability, and Henry showed an example where you had these three pairs of points, and you could express whether there is a common point to the lines that they spawn. So to me that sounds like a question about extendability of representation, right? Can you add that point so that it's on those lines? Now, a question that I find interesting is that if you extend a matroid with an extra point, then it sometimes puts restrictions on the representation you already have. You won't be able to extend every possible representation. Now, what you would like to know is whether this restriction it already is there in a minor of that matroid. You would like to see that added restriction from adding the point. You exactly want to exclude minor, right? You want a small minor already giving you that restriction when you add the point.
It's minimal with respect to.
So the question is, can you perhaps calculate that minor, or it's when
Interesting point, but to fools I have no idea.
It's very close to our conversation yesterday.
Yes.
That is, if you have a restriction of the matroid, can you get the same Whitney algebra if you take the Whitney algebra on the larger one and just take monomials of smaller content, and do all your reduction in the larger one, just restrict that, and the answer was no.
The
In fact,
restriction,
the properties induced on the subset by the addition of a new point on these three lines actually is not present in the algebra of the smaller set, even if it happens to be a subset of that. You can't detect it from the restrict. You remember you showed me in the Bill Schmidt writing that it was that the restriction of the what?
Yes, there is a proposition in your paper that
Yeah,
the
that's right.
restriction of the, if you start from set Matroid, a set, consider a set S, a subset T, and you have the Matroid on the set S, Matroid, the restriction of the Matroid on the subset
Right.
T, you will have the Whitney algebras of M, and the Whitney algebras of T, and in your paper there is a proposition that says that you have the inclusion of algebras. This is for the restriction. The problem is for contraction.
Oh,
We don't have idea. There is no proposition in your paper concerning the operation of contraction. Of
Yeah.
Matroid. What is the effect of the contraction operator, Matroidal contraction operator on the Whitney algebra? There is no proposition. No. It is an absolutely interesting point. How? What is the relation between the Whitney algebras of Matroid and the Whitney algebras of the contractions? One point.
With respect to Rudy's question, I'm not sure.
You're not sure.
I'm not sure which side this takes on this question, but that's just confusion on my part.
So what about, it's sort of a slightly different question, but it's something I was talking to Rudy about this. What about the connection between this sort of Whitney algebra sort of thing and algebraic representability instead of linear representability? Is there anything that you can, any insight you can get there?
For algebraic representability, I have no feeling of algebraic representability.
Yeah.
Hard to imagine how this could encode algebraic dependence. It's pretty
It's not,
linear,
it's,
isn't
yeah,
it?
it's not.
Well, somehow, but this is just a feeling,
Yeah.
a rough feeling. One can think that if you have a vector space representations, somehow in the superalgebraic setting, you are working with negative symbols.
Yeah.
Somehow. Don't know, maybe if you are considering algebraic representations, you are considering positively positive
It's just that,
symbols, and so you may have a superalgebra that mixes things, but this is just
no, it's just that I've always thought if you want to see true horror, you know, you don't go to the movies. What you do is you start thinking about how to solve problems in algebraic representativity. And I was just sort of, every now and then I have a mild fantasy that someone or something they will give us a handle on the true horror of it. It's probably won't help.
Right, well, thank you, Francesco.
Thank you.